So, good afternoon, students. Since we are ready for today's class on artificial neural network, and obviously, as we all can remember that we have left that particular class in the previous day on a particular note, where basically perceptron has been used to solve a linearly separable class. And we have taken an example of, OR function, and we have shown that how this particular simple perceptron, that is a single layer feed-forward network, and it can, utilize its learning to segregate the linearly separable classes. So now, coming to the perceptron, as we all know that it has, certain limitations as well, because it is a very simple neural network. It is the simplest one, you can say. So what are the limitations, that a perceptron can be? As we all know that the OR function can be treated as linearly separable function, and that is why this particular function can be classified by perceptron neural network. So apart from this OR function, two more functions are there. Those are Boolean functions, which can also be solvable by this perceptron neural network, and that those functions are also linearly separable. Those two functions are AND function and complement function. So what does this particular information try to, address us? That is, this perceptron neural network can only model, linearly separable functions. That means the functions who can be, graphically represented in two-dimensional graphs. And if you can draw a straight line, you can separate these, functions as it is holding the values in two parts. One is truth values and obviously the false values as outputs. That means in that manner, there is a particular, situation from where we can conclude that means every time we are saying that the particular, perceptron neural network, cannot, I mean, it's very much, required that we should follow the particular, linearly separable classes. So that means automatically we are trying to say that this nonlinear separation classes, that means those classes are not, separable linearly, or you cannot, obtain this particular, separable classes by drawing only a single straight line. Then in that particular cases, this perceptron, fall apart. And this particular perceptron neural network then cannot, separate those classes. Those are nonlinear classes. So if we can have the liberty to show that whether we have such kind of, function, then automatically we can, take an example with a very popular, with our, very well known XOR function, which is a non-linear function. That means this particular function gives you outputs which are non-linearly separable classes. So can we have that particular example? So what this XOR function is all about, that I want to recapitulate, although we all know about it. So basically, this is nothing but a non-linearly separable function, which basically computes, the Boolean logic functions of, exclusive OR, right? Exclusive OR. And what happens that this function, takes the input arguments with values in 0 and 1, because we know that all the Boolean functions like AND functions, like OR functions, like XOR functions, like XOR functions, we usually represent all these Boolean functions by utilizing only two variables, two input variables. That means one is one you can say as x1 and another you can say as x2. Now, what happens that in case of, dealing with these two input functions, automatically we can expect also only one output value, which is, you can say, that is those output values which, comes into a closed interval like 0 and 1, because we have no other option but only to choose any binary outputs, either 0 or 1. And we all know that these zeros and ones are nothing but the truth values as false and true here in case of, soft computing logic. And output, we know that is true only if the two input values are holding, different truth values. That means whether it is a 0-1 combination or it is a 1-0 combination, only for these two, combinations, that XOR function can provide you a truth value of output, that means a 1. Otherwise, in both the cases where the input variables are just similar to among them, so basically in that case, the particular XOR function is giving you the 0 output. That means for 0-0 case and 1-1 case. Now, if it is a nonlinear separable function, can we, infer it from the graphical representation as we did for the OR function in the previous class? Obviously, we can do. How? For that reason, we need to draw the XOR function in a graphical mode. So if you can see here that this particular table, represents the XOR function, where x1, x2 are treated as inputs, all we know that. And here we can expect 4, input combinations, as you can see that 0, 0, 0, 1, 1, 0, and 1, 1. And automatically for each input combinations, you can have an output values, which is x1 XOR x2, that is for both the cases as depicted in the table. For the combination 1 and combination 4, for these two combinations, outputs are zeros. And as we all know from the truth table of XOR function, that is for, the combination 2 and combination 3, the outputs are given as 1. Now, what happened when we are going to, represent this particular function graphically? So here, as we have done in previous class as well, so basically this is the point where this x1 and x2 are both holding 0 values. So basically this is false. And this is one particular point, where this x1 and x2 both holds 1 value, right? So basically these two are the similar classes. These two are the similar values that should, come into one class, or that should fall into one class, right? So that class label is false. So what happens that we can have a particular, false region here, and we can have a true region like here and here. Suppose this is a point where x1, this x1 is having, 0 value, but x2 is having 1. So automatically this is somewhat your 0-1 combination, which gives you a true value. And here basically your x1 is holding 1, but your x2 is holding 0 value. So basically it is a 1-0 combination for which you are getting a 1 or true value. So how can you combine now? How can you, these two are the similar class labels. So automatically those two values must, fall into one particular class, so that we can, combine each of class, or we can segregate each of class, in that manner, so that all the similar type of class should fall at one particular side, like we did in the OR function. But here you can see that by drawing only one straight line, it is very difficult, it is somewhat impossible to, segregate two classes, because here the two classes are not linearly separated. They are non-linearly separated. So what to do? We can do is, we can, take this particular example so that we can have to, create one linear separator. We can, we can design in such a way that we can obtain a linear separator, which is a non-linear one, but it looks like a linear separator, which can at least, try to segregate the non-linearly separable classes. So what happens that for this particular, situation, you can see that what a feed-forward neural network do for having, whenever it has a kind of, XOR function. So basically what has that this is a kind of, feed-forward neural network. That model is very much, known to us right now, because we have already, covered that particular phase, that how does the feed-forward neural network look like. So basically this is a feed-forward neural network. And as you can see that here we are trying to, create a, a kind of, multi-layer, feed-forward neural network. Why? Because here we are going to have one input layer, that is x1, x2. This layer is treated as the hidden layers, that is h1 and h2. And this is one output layer, which is y. You can say one, that means here, as I have already given you one assignment on a particular, question, that if you want to draw a particular feed-forward neural network or supervised learning network by mentioning a number of neurons at each phases, so it will look like this. That means we have two neurons at the input stages, two neurons at the hidden layers, and obviously one neuron at the output stage. Now what happens that let us assume that this is the weight, the weight which is associating with the connecting links, which is coming from x1 to h1 is 20. That means a positive 20. This is a plus 20, which we know that we can have, positive as well as negative values for this artificial neural network. The weight value for this particular link is also 20. For this is minus 20, this is minus 20, this is plus 20, the connecting link, which comes from H2 to Y, which is an output neuron. And this is also plus 20, which is coming from H1 to Y. And you can see here that we have to bias, right? We have to bias. One bias value is minus 1. Another bias value is minus 30. So what you have here, that you have to, consider bias value as well, because we know that whenever we have bias, how does our, neural network look like, or we can, how we can, compute the particular expression. That is nothing but 20x1. That means we are going to compute the expression for this node, that is h1. For this, basically this is 20x1 plus 20x2 minus this bias, that is minus 10. The weight is, we know that the weight is basically 1, right? Now what happens, that means here we can have a particular this kind of x. So now moving further, so if this is understood, then we should go further in the next slide, and we are going to, determine all the expressions which are associated with, the rest of the neurons. So what it happens that here, basically, if you now try to, compute what are the expressions that is associated with this neuron and this neuron, that means the hidden layer neuron H2 and the output neuron Y. So what it happens that basically for H2, now we are going to try to compute this, as you can see very much clear that this is something like minus 20x1 minus 20x2 plus 30, because this bias is having the positive value, right? And for this is quite interesting. because this is now the output neuron, right? Y, and it has a basically this connecting link, shares the information which is holding in the hidden layer neuron H1 and the output neuron Y. So what happens here, that whenever you are going to compute this particular, the output expression of this particular node, or we can say neuron, it is having 20 H1, right? Because the link is coming from H1, not X1 here, because that is why we are talking about the multi-layer, perceptron. This is a multi-layer perceptron, a multi-layer feed-forward neural network. You can say anything. So here you can see this is 20H1 plus 20H2 minus 30, because this particular neuron is having the base value as minus 30. Now, so we have achieved, these three expressions. So what we need to do is now, we need to now compute for all the input combinations, as we know that how the perceptron, works. So basically what we are having to do is, we can have 4 input combinations. We know that, from the previous slide, that is from the, slide where we are going to have this particular, truth table. So what we can do is, we can have, 4 possible combinations, and we are going to try all those possible combinations to basically compute what is the value of the output node. That means what is the output we can obtain, from Y. So here, starting from the first left hand side one, what we have here, we have taken the X1 value as 0, X2 value as 0. That means we have computed this particular thing for 0, 0 combination. So what you will get obviously from here as a result of minus 10. And as if you can remember, the previous class, that if we are getting a minus value, that is a negative value, that means the output, if output is less than 0, then automatically we are treating that output must be labeled as 0. And if we are getting the positive value, positive output, that means the output which is greater than 0, then automatically we can label that particular output as 1, as the class level 1. So here it is. And then since we are getting minus 10 here, so automatically this class level must be 0. That means the output is 0 here. Here we are getting 20 plus 20, that is 40, minus 10, that means plus 30, which is a positive one. So automatically we can approximate that class level by the output 1. Now here, here what you can see is the same manner. This is, this is for H1. Now this is for H2. This is for H2. By taking the same combination, the first combination, which is 0, 0, that means here you are getting plus 30. So automatically this must be 1. So now for first combination, that is the 0, 0 combination, input combinations, what we get here, that we are getting, H1 as 0, H2 as 1, right? Because this is a computational expression for H1 for 0, 0 combination. And this is the computational expression of H2 for 0, 0 input combinations, right? So what we have got here, we have got, a kind of H1 equal to 0 and H2 equal to 1. So now we are ready to, compute what should be the output from this Y node or Y neuron. So by putting the value of H1, which is 0, and putting the value of H2, which is 1, you can see here, we are getting 20 minus 30, which is minus 10. So automatically for a negative value, we will get 0 output. Coming to the next input combinations, which can be a 1, 1. That means the fourth one, the last combinations, which we can expect in our very own, truth table. So basically, taking this 1-1 combinations, easily you can see now, you can understand well why this 1 has been written, because this is 40 minus 10, which gives you the plus 30. Here it comes 0 for H2 by taking 1-1 combination, 1-1 input combination. That means X1 is 1 and X2 is 1. That means this is minus 40 plus 30, which means it gives you the minus 10. So automatically output will be 0. And now for this 1-1 input combinations, now you have got the H1 as 1 and H2 as 0. So what you can, expect here, you can put the H1 as 1 and H2 as 0, and you will have an output which gives you a minus 10, because 20 minus 30, that means it gives you minus 10. So automatically the output must be 0. Now you can see that this is the logic right behind the truth table of the XOR function, where we can expect 0, 0 output values for, similar input combinations. That means whenever we are taking 0, 0 input combinations, or we are taking 1, 1 input combinations, we always get the zeros as the output value. Now coming to the, input combinations which are dissimilar. That means with those combinations which, provide you the output as 1. Coming to one such combinations, which is a 0, 1 combination. By taking 0, 1 combinations, by following the similar manner what we have just explained in the previous slide, you can get, 20 minus 10, that is the plus 10. So you have 1, 1 here. You're having for H2 for 0, 1 combination as minus 20 plus 30, which is also a plus 1. I mean positive 10. That is why 1 plus 1 you have got as the output. And for this particular combination, that means for 0, 1 combination, you will have now the H1 as 1, H2 as 1. So by putting this 1 and 1, you are getting, 40 minus 30, that is 10. And you will have an output as 1. Now, going further, simultaneously, I will request you to give you all your attendance. And this is the last, last input combinations of our truth table, which gives you a kind of, combinations like 1, 0, which is another dissimilar combinations you can see. So here, what happens that whenever we have that kind of combinations, so we can have 20 minus 10, that is plus 10. So that is why we can put here 1. Here we can have, minus 20 plus 30. So that means plus 10, for which we are having 1 for H2. So for this particular combination, that 1, 0 combination, we will have H1 as 1 and H2 as 1, so that we will get an output from this Y node is like 20 plus 20, that is 40, and minus 30, that means which gives you the 1. Now what happens that if this particular things are finished, so now you can understand that how this feed-forward neural network is working for XOR function. Now, so coming, what is basically now the multi-layer feed-forward function? That is the the FN, this particular multi-layer neural feed-forward neural network. This FFNN, this is a short form or abbreviated form of this particular neural network. So this is basically the more general network architectures, which is which can be understood well, and where we know that the particular difference from what we had in our single layer feed-forward neural network is we have here hidden layers between that input and output layers, and obviously those hidden layers can be from 0 to several. So basically hidden nodes here, what those nodes are present, are very much present in the hidden layers. Those nodes, do not directly, receive inputs, not send outputs to the external environment. For doing so, basically we need to, rely on the input layer as well as output layer. So we can say that how we can measure the complexity of the neural network in this case of multi-layer feed-forward network. So in that case, what we need to do is we can, if we can, maximize the number of hidden layers, then we can, you know, increase the complexity of the network by incorporating more number of hidden neurons in the hidden layers, because the all the computation task is basically taking place in this particular layer, that is the hidden layer. So in this manner, by incorporating the hidden layers and hidden neurons, and automatically whenever this multi-layer feed-forward neural network can be suitable for dealing with the non-separable, non-linearly separable classes. So basically in this manner, FFNNs also, overcome the limitation of a single layer neural network. So basically they can handle non-linearly separable learning tasks very well. Now, so this particular neural model, so this particular classical learning algorithm, which is basically associated with this kind of neural model, this is, basically follow the gradient descent method. This is one, beautiful method, which is going to be described in the next slide. What we need to do here is basically why we require this kind of method. Because we basically, what we have that whenever we have such kind of activation functions, that means starting from step function, starting from signal function, starting from Gaussian function, you can say. So what happens then, somewhere this activation functions are a continuous function of weights. So if it is a continuous function, so we know that it can be differentiable everywhere, right? So by the help of this particular nature, to avail this particular nature to differentiate those activation functions on the neuronal dynamics everywhere, we need this particular gradient descent method. So what kind of representation this particular activation function hold, that you can see that for node I, for a particular node, let's say I, that is defined as a very simple form of sigmoid function. And this is a particular representation that here is shown, that is the psi of this vi. If this is a kind of activation function, this is equal to 1 by 1 plus e to the power minus a into vi. Now what is this vi? Vi is every time just going to be updated, and we know that this particular vi can be computed like summation of wij into yj. Now what is yj? Yj is nothing but the output of node j. That means obviously every time we have some connecting link which shares the connection from node I to node j. So that is why here weight matrix or weight values, weight vector, you can say those values are basically particular, represent the particular value of the weight vector which is coming from the node I to node j, and this yj is whatever be the the output of the next node, that means the node j. So basically this is one kind of sigmoid function which can be treated as the activation function for this particular feed forward neural network. So this is how this gradient descent learning method looks like. That means if you can roll a ball, if you can roll a ball, and if this is the starting point, then this must be the w0. And if particular, at a particular time instant, after a certain period of time, if that particular ball resides at this particular point, stays at this particular point, then how can you determine what is the weight or particular, weight of this neuron at this particular point? So then this wn, by following this gradient descent learning, this Wn can be computed as W0 minus eta of del E by del W. So del means obviously all of you we can know that this is a partial differential function. So that is why it is written here that this gradient descent learning method tells us that everywhere that particular thing is differentiable. So where eta lies in 0 to 1. So this is a first order iterative, optimization algorithm which follows this gradient descent learning method so that we can find the local minimum of this particular function where we can take approximate gradient. That means this approximation values by taking the partial differentiation method. So this is how you can expect a particular 2 marks or 3 marks question that what do you mean by gradient descent learning method. Now this is all about the single layer and multi-layer feed-forward network. But what about the single node with its own feedback network? Which is, you can see here that this is one, single node. It is having a single node and it is having only its own feedback where the outputs are directed back as inputs to the same or the preceding layer nodes. So basically recurrent network, the concept of recurrent network will form here where the network consists of closed loop. So here basically the figure represents a simple recurrent neural network having a single neuron with feedback to itself. So this is what single node with its own feedback. This is single layer recurrent neural network where you can see the processing elements output can be directed back to itself or to other processing elements or both. This is a single layer recurrent neural network. And this is the last slide, which is multi-layer recurrent neural network where processing elements output can be directed back to itself or to other processing elements or both. So basically